Yeah, hello everyone. So as mentioned, my name is Yaroslav Alekseev, and I'm a PhD student from the Technion. And before describing the actual results of our paper, I would like to give you a brief overview of the area, and after that we'll get to the result itself. So what is a k-independence? Suppose we have a distribution over a Boolean cube, and we say that it's k-independent if for every subset of the variables of size k, and for every substitution of this variable, probability that our vector sampled from this distribution over the set I is equal to alpha is equal to the 2 to the minus k. So here is a simple example of such distribution, which is k-independent, but is not just independent in general. So suppose we have like we define the polynomials that way. So the coefficients of the polynomials would be y's, where y's are sampled independently uniformly from fp. And alpha would be the indexes of our elements of our vectors. So now we know that if we take any k points xi, then they uniquely determine yi, etc., y1, etc., yk. So it means that if this y's were sampled uniformly, then the probability that those values are of x from I is equal to some constant is exactly 2 to the minus k. So it makes them not 2, 1 over p to the minus k, which makes them k-independent. Also, we can define the following things. So if we have a circuit C, then we say the distribution mu epsilon fools circuit C if the probability that C is equal to 1 is almost exactly the same as probability that C is equal to 1 if we sample X from the uniform distribution. So simple observation is that if measure mu is k-independent, it's equivalent exactly to the fact that this measure 0 fools k juntos. So the priced result of Braverman is that log m to the OD log 1 over epsilon dependent distribution, epsilon full size m depth d AC0 circuits. Also, we know that poly 1 of dependent, like poly 1 over epsilon independence, epsilon fools half spaces. I have a fancy animation here. Now I would like to describe what the almost k-independence is. So suppose that distribution mu over Boolean cube is, we say that it's epsilon k independent if for every subset of elements of size k and for every value alpha of this from 0, 1 to I, the probability that xi is equal to alpha if we sample x according to mu belongs to the 2 to the minus k multiplied by y minus epsilon to 1 plus epsilon. So we know for a fact that the size of the support of any like k-independent measure mu is 2 to the k n, at least 2 to the k n. That means that if we try to randomize it naively, it will take a super polynomial time for us. So, however, if there is a construction of epsilon k independent set over measure over Boolean cube such that the support of this measure is at most n to the 2 to the k divided by epsilon squared. So in some sets, it's better. So there is a hope that it might be easier to randomize that kind of distributions. So Aronson proves that there is a n to the almost n to the omega of 1 independent distribution over Boolean cube that can be distinguished from the uniform by a log of 1 and depth quantum decision tree. And also in the same year, he conjectured that almost k-independence full AC0 circuits. And yeah, he also put a price on this conjecture. And he showed that this conjecture would imply the BQP doesn't belong to PH if we add an oracle. However, this was proved independently by Riazanov in 2018. And this particular conjecture turns out to be false. So Aronson shows the following simple counterexample. So he showed that there is a distribution mu that is almost 10 to the omega 1 independent, and also 1/2 distinguishable from the uniform by depth 3AC0 circuit. So what was his example? It was quite simple and still, but elegant. So, and in some sense, it was an inspiration for our paper, like this particular example. So first we sample an element from n to the n log n. So here is here is like the position of the element, and the bottom is the value of this element. So it's like an array. Then we pick uniformly random I from the n. And then for each j that belongs to the n log n, such that ij is equal to I, we sample this particular value ij such that it belongs to n minus I. So here, like as a fancy animation, how it works. And now we know that it's like this function, a from, like, it's not surjective. So there is at least one value that is not covered by like the support of our set A. So how can we check it with like, I'm sorry, how can we check it with a, how can we check it with a depth-free circuit? So we just check whether the function like a1, etc., n log n is surjective by the following depth-free circuit. And on the other hand, it's easy to check that the distribution that we get would be n like almost n to the omega 1 independent. So that was the inspiration for our result. However, there is still like open question after this counterexample. So we know that almost n independent, like n to the omega 1 independent sets, that this conjecture is false for the depth-free circuit. But what about DNFs? So in this work, we showed the following, that there is a distribution mu that is n to the omega 1 independent and 1/2 distinguishable from the uniform by of log to the 3n with DNF. So that's the main result of our paper. So how are we going to construct this counterexample? We start with the indexing function. So what is the indexing function? On the left-hand side, like on the, it operates with like with the index and with the array. So it takes index, it's a set of, it's like an array of size log n, and array is like size of n. So here, for example, index encodes the value 5. So it's like it's just a binary notation, Boolean encoding. And then it means that like this index points to the position with the index 5 in our array. And here in this position, we have 1. That means that our indexing function outputs 1. Now, we can prove the following claim, that if we consider the pre-image of 1 of this indexing function and restrict it to the array and take a uniform distribution over the set, then it would be 1 over square root n independent. Why is that so? So it's sufficient for us to prove only the lower bound because everything is symmetric here. So we need to show that we need to prove like a lower bound on the probability that the array of I is equal to alpha for any I of size square root n and for every substitution alpha. So this probability, it is greater than this conditional probability multiplied by probability that index doesn't belong to I. So the first thing is equal to the 2 to the minus I, and the second one is equal to the 1 minus 1 over square root n. So this gives us a lower bound. And in a similar fashion, we can prove like an upper bound because everything is balanced. However, indexing function alone is not enough for us to construct a counterexample. Why is it so? Because if we consider like the full image, so if we consider like both index and array from the pre-image of minus from 1, then, for example, probability that here it is shown like explicitly. If we consider some fixed value on the left, and if we add to the I the corresponding element that's like has the index with this layer, then the probability that, for example, here index of 10 and array of 10 is equal to 0 is 0, which is not good for us. We need a lower bound of this probability. So how are we going to fix it? So we like our first attempt would be to substitute tribes function instead of the instead of the indexing part of our domain. So what is the tribes function? So here it's output 0 if it works with with the matrices by some size of roughly log n by n, and if output 0 if it has this matrix has at least one column which consists of all ones, and 0 otherwise. And we know if you carefully choose parameters for this matrix, then the distribution of this function of the probability that this function is equal to 1 is close to the 1/2. So the problem with this composed function is the following. First of all, we don't know how to do, we cannot recognize it with DNF. And secondly, we're not sure that it's almost the n to the omega-1 independent. So how are we going to fix this issue? We are going to consider the monotone indexing function composed with this tribes function. So we restrict our inputs to the, in some sense, to the only to the case where the Hamming weight of the index is equal to the log n divided by 2. Then, how are we going to construct our DNF? So we know that the DNF, the width of the DNF is the same as the size of the certificate for the one, the biggest certificate for the one values of our function. So here to certify the fact that we have a one value, we just pick the corresponding some of the corresponding columns from for the indexing function, and it will require us log n to the free space. And then we make sure that if the Hamming weight of indexing is less than log n over 2, our value is always 0, and if it's greater than log n over 2, then it's always 1. And that would be enough for us. And then you can just check it, whether it works or not, and it will just work. So, yeah. Given that, we only have a few open questions. So first of all, we need to find the polynomial size. We're not sure, we have a DNF of the width log 3 to n, polylog width, but we cannot make sure that the size of the DNF is a polynomial. So can we find a polynomial size DNF distinguished in an almost k-independent distribution from the uniform? And the second question is, can we show, with a top-down argument, that it's hard to depth-free circuits, ACDR circuits, to distinguish two disjoint k-independent sets? So yeah, I guess it was rather a short talk. So thank you for your attention.